Welcome back everyone. We have studied about the reflection of light through spherical mirrors, and today we will be studying about refraction of light through the spherical lenses. Now first of all we need to know what is a lens. So it is just a piece of transparent glass which has two spherical surfaces, and because it has two spherical surfaces, so refraction occurs two times. Once when it passes from air into the glass at this surface, then from glass back into the air at this surface. So two refractions will occur. In this lens, both the spherical surfaces are bulging out, so we call it as a convex lens. In this, both the surfaces are bent in surfaces, so it will be called as a concave lens. But we define the lenses as a convex lens is that which is thicker in the middle but thinner at the edges, while a concave lens is that lens which is thinner in the middle but thicker at the edges. A convex lens is a converging lens, means if parallel rays of light will pass through it, they will bend towards the principal axis. If parallel rays will pass through a concave lens, they will bend away from the principal axis. So it is a diverging lens. Now we will see how to identify the type of a lens. Now this lens has two spherical surfaces and both are bulging out, so there is no problem, we know it is a convex. Now in this case it has one plane and one concave surface. It has two concave surfaces, it has one convex, one concave surface. So in such cases we will simply go by the definition of a lens. So we know that lens which is thicker in the middle will be a convex lens. So let's identify among these lenses. This one is thicker in the middle, so it is a convex lens. This one is thinner, this is also thinner, but this one is thicker in the middle, it is a convex lens. This is also thicker in the middle. Remember, we have to compare the middle part with the edges. So it is thicker here and thinner at the edges. So it is a convex lens. So rest three. This is thinner in the middle, thinner in the middle. This one is thinner in the middle but thicker at the edges. So these are concave lenses. So this is how we identify the type of a lens. But now how to name? If it has two convex surfaces, biconvex, two concave surfaces, biconcave, one plane and one concave, plano-concave, this is one concave, one convex and one concave. It is concavo-convex, it is plano-convex, it is convexo-concave. Now let's see these two. How to name these two? We will keep the last name of the lens as that according to what it is behaving. So as it is behaving as a convex lens, so last part of the name will have convex. It is behaving as a concave lens, so last part of the lens will have the name concave. So this is how we name the lenses. Let's know about the important terms that are related with these lenses. First of all, we need to know that because a lens has two spherical surfaces, it means it has been made from two spheres. This spherical surface is the part of this sphere of glass, and this spherical surface is the part of this sphere of glass. And same for concave lens also. This spherical surface will be the part of this sphere and this will be the part of the other sphere of glass. So every lens is made from two spheres of glasses. First term is aperture. If we join the two edges of a lens, this vertical line will be called as the aperture of lens, and we define it as the diameter of the circular edge of the lens. As we discussed just now that every lens is made from two spheres of glass and the centers of these spheres are called as center of curvature. So every lens has two center of curvatures, C1 and C2. Similarly, concave lens also C1 and C2, it has two centers of curvatures. Principal axis is that imaginary line which will pass through both the center of curvatures. And optical center is the center of the lens, and it is that point on the principal axis through which if a ray of light will pass, it will go undeviated. It will pass straight without any refraction. Next important term is principal focus. As a spherical lens has two spherical surfaces, two centers of curvatures, so it has two principal foci also. Let's first try to understand it. We learned in case of mirrors that if we place an object at different positions in front of a mirror, image position also varies accordingly. So now we will find out that position on the principal axis for an object for which after refraction rays become parallel to each other. So that position in which after refraction rays become parallel to each other. So now we know that if rays are parallel to one another, it means that image will be formed somewhere at infinity. So now this position of the object for which image is formed at infinity will be called as first principal focus. Now remember three things here. Number one, object should be the point object. Number two, it should be on the principal axis. And number three, image should be formed at infinity. So that point F1 will be called as first principal focus. Now suppose if our object is at infinity, means rays will come parallel to one another and they will pass through the lens and get refracted. Because it is a converging lens, so all the rays will meet at one point. That one point where all the rays are meeting, image will also be formed at that point. So that will be called as F2. So now this is the second principal focus and it is the position of the image for which object is at infinity. So now it has become clear. First principal focus is the position of the point object for which image is at infinity. Second principal focus is the position of the point image for which object is at infinity. Now similarly, first focal length is the distance between the optical center and first principal focus. Second focal length is the distance between the optical center and the second principal focus. We will now see the principal focus for the concave lens and it also has two principal foci. Now these are the incident rays. This incident ray after passing through the concave lens becomes parallel to the principal axis and this one also becomes parallel to the principal axis, which suggests that image will be formed at infinity. Now if we extend these rays in the forward direction, they appear to meet at this point. Now our object, which is somewhere here, it appears to be here. So we consider F1 as the virtual position of the object for which image is formed at infinity. So this F1 is our first principal focus. So we define it as the virtual position of the object for which image is formed at infinity. Now these are the parallel incident rays which suggest that object is at infinity. When these rays pass through the concave lens, because it is a diverging lens, so this ray diverges in this direction and this diverges in this direction. And it is obvious they will never meet in front. But if we extend these rays in the backward direction, they appear to meet at this point or they appear to come from this point where the image will be formed. And we can see that it will be a virtual image. So now this point F2 is the second principal focus. So we can say that it is the position of the image for which object is at infinity. So these are the two principal foci of concave lens. If you have noticed, first principal focus in a concave lens is towards the right side of the lens. But remember for convex lens, it was towards the left side. Now this creates confusion and problems when we draw the diagrams or when we solve the problems related to the lenses. So to make the things simpler and easier, first focal length in both the lenses is taken on the left side, while second focal length is taken on the right side of both the lenses. Though for concave lens we know it is opposite, but for simplicity we take first focal length towards the left side. Now practice these 4 diagrams carefully before you move further. And now you have a question. What are the factors on which focal length of a lens depends? Think about the answer by pausing the video and then you can see the answer. There are various factors on which focal length depends. First is the radii of curvature of the lens, just like in mirrors. In the same manner, focal length of lens is also half of the radius of curvature. It also depends upon the nature of material because different materials have different refractive index and because of different refractive index there will be different extent of bending. So focal length will be different. Third is nature of medium in which lens is placed, whether lens is present in air or it is present in water or oil. So accordingly, focal length will also change. To understand the third factor, let's solve one more question. A convex lens is held separately in air and in water. What changes, if any, do you expect in the focal length of the lens in these two cases? So now this lens is kept in air and this lens is kept in water. Now let's see the speed of light in the two. In air, speed of light is 3 into 10 raised to power 8, but in glass, speed of light is 2 into 10 raised to power 8. So we notice the difference in the speeds, which is quite a lot. As a result, when the difference in the speed is more, bending will also be more. So here more bending has taken place. But if we keep the same lens in water, now notice the difference in their speeds. In glass it is 2 and in water it is 2.25 into 10 to the power 8, which is quite less as compared to air and glass. As a result, bending will be very less. So if bending is less, it means focal length will be more. So now this is the relationship between the focal length and the bending. Lesser the bending, more is the focal length. While discussing various terms and the principal focus of the lens, we saw that there are certain incident rays which follow the fixed path that can be predicted also. Such incident rays are called as standard incident rays, and those standard incident rays which have fixed path to follow can be used as rules to draw the ray diagrams for lenses. So we have such easily predictable three rays which we can use. So first ray is that which is parallel to the principal axis. This ray, after refracting through the lens, will always pass through the principal focus. So this path we know. Second incident ray is that one which passes through the principal focus and after refraction it becomes parallel to the principal axis. So this can be considered as second standard incident ray. Third is that which passes through the optical center. This one passes straight without any deviation. So these three incident rays which have fixed path for the refraction or after the refraction can be used as rules to draw the ray diagrams for convex lens. Now we are ready for the formation of images in case of a convex lens. And I suggest you once again, before you start with the lenses, you must have absolute clarity about the ray diagrams in case of mirrors. Otherwise, you will get confused here. So now convex lens will be taken and an object of finite size, that is AB, will be kept in front of it at different positions, and we will see that where is image formed and what are the characteristics of this image. This object will be placed at these 6 different positions, which are at infinity, then beyond 2f1, at 2f1, between f1 and 2f1, at f1, which is the first principal focus, and between optical center and first principal focus. You must be wondering what is 2f1. Now here 2f1 is twice of f1 and it is also equal to the radius of curvature of the lens. First position of object is at infinity. Before we start with the diagram, remember one more thing. In a spherical lens, as I have already told you, that refraction occurs twice on both the surfaces, but we are not going to show the refraction 2 times, but we will be showing it only once, and that refraction will occur from this central line. Means incident rays must come up till this central line and bending will be after this line. So now let's start with the diagram. When the object is at infinity, we know that rays will come parallel. If the rays are parallel to the principal axis, from this line they will converge because it is a converging lens and they all meet at one point. And we know wherever the refracted rays will meet, image will be formed there. So for this diagram, the characteristics of the image will be: position of image is at f2, its size is point sized and it is real and inverted because rays are actually meeting. Now there is another situation when rays are parallel but they are not parallel to the principal axis. So in this case we have drawn two rays. Out of those two rays, one must pass through the optical center, because we know the rays that pass through the optical center, they pass straight without bending. Now the second ray will bend from here, but we know that image has to be formed at principal focus. So we'll bend it in such a way that it meets the other ray at F2. Now join F2 with the principal axis and this is our image. And the characteristics are, image is at F2, it is highly diminished and it is real and inverted. We will now bring the object closer and place it beyond 2f1. Now in this case we need to take proper measurements of the lens, which will be in 4 lines, and all these distances O and f1 3 centimeter, this distance 3, all these distances will be 3 centimeter, and height of our object will be equal to 1 line of the register. Now we know that to find out where the image is formed, we need only two rays, and wherever those two refracted rays will meet, image will be formed there. And we will make both the rays from the point A. Apply rule 1 first. A ray which is parallel after refraction will pass through F2, and we will apply now rule number 3. The ray which passes through optical center will go straight and undeviated. Wherever the two rays cross each other, image has to be formed there. So we'll join this point with the principal axis and A dash B dash will be our image. So we can easily see that this image has been formed between F2 and 2F2. Then we will compare its size with the size of the object and we see that it is slightly smaller. So it is diminished and it is real and inverted. Next position is at 2F1. I suggest you to use a sharpened pencil here and apply rule 1. The ray which is parallel to the principal axis after refraction will pass through principal focus, and the ray which passes through the optical center will go straight undeviated, and we will see where these two rays are meeting with each other. So image will be formed here. Join this point with the principal axis and this is our image, and we can see it has been formed at 2f2, and if height of our object was 1 line, its size will also be equal to 1 line. And do not forget to put these arrows to show the direction of the rays. So the position of image is at 2f2, size same as that of object, and it is real and inverted. Our next position is between f1 and 2f1. So keep the object here. First ray which is parallel will pass through f2, second will pass through O undeviated, and wherever the two rays will meet, we will join it with the principal axis to form the image. A dash B dash is the image. We can see it has been formed beyond 2f2. Size, compare it with the size of the object. It is magnified and it will be real and inverted. Bring the object closer and keep it at first principal focus. And again the same two rules will be applied. Parallel ray will pass through f2. One which passes through optical center will go straight. And see the two refracted rays. They are parallel to one another, which means that they will meet somewhere at infinity and image will also be formed at infinity. So image is at infinity, it will be magnified and it will be real and inverted. Now we come to the last position of the object, which is between the optical center and the first principal focus. Height of our object is 1 line and first ray parallel to the principal axis will pass through f2. Second ray will pass through optical center and it will go undeviated. Now we can see that these two refracted rays, they appear diverging, so they can never meet in front. But if we extend them in the backward direction, both the rays, they will meet at some point. And wherever these two rays meet, if you connect this point with the principal axis, our image will be formed there. So now A dash B dash is our image, which is the virtual image because rays are not actually meeting. So it is a virtual image. Position is on the same side of the lens. It will be highly magnified and it is virtual and direct. Now these are all the diagrams that we have drawn for the convex lens when the object was placed at different positions. And we will draw a few conclusions from these diagrams. Here in this case, real and inverted image is formed. Here also real and inverted, here also and here also. So we can see in first 5 cases real and inverted image has been formed. But in this last case virtual and erect image is formed, and we know in this case object is placed between optical center and first principal focus. In rest all the cases when object was between infinity and first principal focus, in all these cases image formed is real and inverted. And our second conclusion is about the distance of image from the lens. So when the object was infinity, image was at principal focus. Object brought closer, image moves away from the principal focus. Then it moves further away and further away. So as we bring the object closer to the lens, image moves away from the lens. Third conclusion is about size of the image. Here it is point sized. Here slightly bigger, more big, and further more big. So as the object is brought closer, size of the image keeps on increasing. So these are few conclusions that we have drawn. As the object moves closer, distance of image from lens increases, size of image also increases, and virtual image is formed only when object is between the principal focus and the optical center. Just like we have seen in case of a convex lens, there are certain standard incident rays whose paths are fixed and they can be easily predicted also. So same are the standard incident rays for a concave lens also. Now the first such ray is that which is parallel to the principal axis, and after refraction it will diverge in such a way that it will appear to come from its principal focus. Second incident ray is that which is directed towards the principal focus, and after refraction it will become parallel to the principal axis. And third one, which passes through the optical center, will go straight undeviated. So these three standard incident rays can be used as three rules to draw the ray diagrams for a concave lens. First position of the object is at infinity. If the object is at infinity, rays will come parallel to the principal axis, and after refraction through the concave lens they will diverge because it is a diverging lens and they can never meet in front. If we extend them in the backward direction, they will appear to come from this point F1 where image will be formed. So the characteristics are position of the image is at F1, it will be highly diminished or point sized, and it will be virtual and erect because we can see rays are not actually meeting. So it will be a virtual image. Now the second is if the object is placed anywhere between infinity and the optical center, anywhere if you keep the object, whether at F1, 2F1, wherever, the image will be formed in the same manner. So let's see, we will apply first rule. This is our object of finite size AB. First incident ray is the ray which is parallel to the principal axis. So after refraction it will diverge in such a way that it appears to come from principal focus. Now we'll use rule 3, another ray from the same point A which will pass through the optical center, and this ray will pass straight. We have to see where two refracted rays are meeting with each other. So this refracted ray has gone this side, but we have extended it backward, and this has come back along the same path. The two rays are meeting here, or they appear to meet at here. So image will be formed at this point. Join this point with the principal axis, A dash B dash will be our image, and we can see that it is a virtual image. So position of image is between F1 and the optical center. Size will be diminished and nature of the image will be virtual and erect. It's the question time now. How will you distinguish between a convex lens and a concave lens without touching it? So we'll keep both the lenses on a printed page and try to read the print. If the print appears magnified, then it will be a convex lens. If the print appears diminished, then it will be a concave lens. Another question, how should you arrange two converging lenses so that a parallel beam of light entering one lens emerges as a parallel beam after passing from the second lens? Now you need to pause the video, read the question again and try to arrange the lenses in this manner. So this will be our answer. We will arrange the two lenses in such a way that f2 of lens 1 and f1 of lens 2 should coincide with each other, means F1 and F2 should lie at the same point. Another question, if one half of the convex lens is covered with the black paper, how will this image be different from the one formed by a normal lens? So I have drawn the diagrams for both the situations when we have covered the lower half of the lens and when we covered the upper half of the lens. So we'll apply rule 1. A ray which is parallel will pass through F2 after refraction. A ray which is passing through the optical center will go straight, and these two rays will be meeting here. Now we'll make a third ray. Any ray after refraction through the lens, it will also meet at the same point. So image is formed here, and we will see that how this image is now different from the image formed by a normal lens. First thing is that a complete image will be formed because the rays are meeting at this point, so a complete image is formed. But the intensity or brightness of the image will be less because half the number of rays are not reaching here. So brightness or the intensity of image will be reduced. Similar is when upper half is covered. Here also we have applied ray which is passing through optical center has gone straight. The ray which is passing through the principal focus, after refraction it becomes parallel to the principal axis. Then we have made a third ray also, make it pass from any point. After refraction it will also join at the same point where the image is being formed. Now remember here, we have used this ray which is passing through the optical center only to know where the rays will meet with each other. So I hope you have understood it. We'll continue in the next video, and please subscribe to the channel.